All right, final review video of the year, and this is on statistics. Starting off the top, difference between observational studies and experiments. Observational studies have participants that are randomly selected to represent a population. So we have a sample from a population. Our participants are observed only, and nothing is done to intervene with their normal behaviors or characteristics. And they are used to describe large populations. So we take a sample from a population, observe it, and we use that to make inferences about a population. So again, nothing's done to them in an observational study. Experiments are a bit different. That's where subjects are randomly assigned into two treatment groups, or three. So you need assignment into at least two groups here. And subjects are acted upon with some sort of intervention. Most of the time, it's usually some sort of drug treatment or a certain type of food that they're ingesting, but essentially we're looking for something that would influence the way that a participant may respond. Cause and effect can be concluded from experiments, and this is the only time cause and effect can be concluded. So keep in mind that when you see something is said to cause another thing, that means an experiment must have been conducted. Okay, so observational studies cannot conclude cause and effect. I'll write C and E for cause and effect. Okay, experiments can. All right, so starting off the bat, an apple juice processing plant receives a truckload of apples. The quality control team randomly chooses 3 pails of apples, each containing 80 apples from the truckload. Is this an observational study or experiment? Nothing is being done to the apples, we're simply observing them, so this is an observational study. The sample is the 3 pails. The population is the truckload. State one conclusion that the quality control team can make about the population if 5% of the sample is found to be unsatisfactory. So guys, what that means is from that truckload, only 5% was bad. This has nothing to do with statistically significant versus not that we talked about later in experiments. This is simply, hey, 5% of your population or 5% of your sample is bad. What might then be true? The only thing you can conclude in an observational study is an inference about the population. So we said the population was truckload. So if 5% of our sample is bad, we can conclude that 5% of our truckload is bad. Okay, so it really doesn't matter what this percent is. It's almost tricky that we do include 5%. I could have made that 20%, 72%. Whatever that percent is of your sample, you can then infer that it might be the same for your population. Describe how a controlled experiment can be created to examine the effect of the amount of sunlight, direct versus indirect, on the growth height of a daffodil. So basically, let's say you have daffodils. You would want to randomly assign them into 2 groups. So random assignment must occur. What's the difference between these 2 groups? We would have one group receive direct sunlight, and the other one indirect. So in doing so, our response that we would measure would likely be the then height of our daffodils. And then I'll say like after a week, because we want to give it time for the daffodils to grow. Okay, so key things you need to make sure that you understand in this problem. When you're running an experiment, you need to have random assignment, and there needs to be some sort of treatment. So in this case, our treatment is the direct versus indirect, and then we need to have a response. So we're measuring the height. So on a Regents question, those are the things that they would be looking for. All right, so I skipped ahead in our packet to question 6. This is a good place to talk about simulations. According to AAA, 46% of all teenage drivers admit to texting while text messaging while driving. Suppose that you ask a random sample of 40 teen drivers if they text and drive, and you record the proportion that say yes. You repeat this process 100 times and display your findings using a sampling distribution as shown below. Okay, so what does each dot on the distribution represent? Each one of these dots is technically a p-hat. It's a proportion of teen drivers that said that they text and drive. So I'm going to write down the proportion of teens that admit to texting and driving out of a sample of 40. So each one of those dots is representing 40 people that you asked, and then the proportion of which that admitted to doing so. So for example, like right in like the center roughly here, I have like 53% we'll say. So of your 40 people, 53% admitted to texting and driving. The shape is approximately normal. The center is roughly in the middle here around like 0.46 roughly, which would be matching that mean up here. Okay, I'm not going to write that down, but just talk about it. Now let's say you collected 100 more samples. How would the center and standard deviation or spread change? Well, it really wouldn't. If you go out and collect more samples, it would just simply fill this in more. It wouldn't really change the mean or standard deviation much at all. All right, to prove this to you guys, I pulled up the simulator just to show you how this works. I set the success to 40%, sample size of 40. Wait, what was it? It wasn't 40%. What was it? 46%, excuse me. 46%. Okay, sample size of 40 on 100 samples. Okay, so there's our distribution. That's 100 dots. A little bit different than what we have in the notes. That's okay. But watch these two numbers as I just add more samples to the distribution. So you'll see that the center is still roughly around 0.46 and the standard deviation is around 0.08. There's a little bit of fluctuation in there, but in general, just me adding more dots really doesn't change it. Okay, and that's after 6,800 samples. Now, the next part of this question says, well, what if you started over and sampled 120 teen drivers? Okay, so if I change this to 120 instead, well, I'm sorry, 100, I want to change my sample size to 120. Watch what happens. Okay, so in comparing it to the one in the notes, the standard deviation here is 0.041. In our notes, it's 0.078. And if I keep drawing more samples, okay, again, you won't see it change much, but you'll see I have that smaller standard deviation in comparison to when I started with a sample size of 40. So let me pull back up the notes quickly here. Okay, so what if you started over? How would the center and spread of the sample compare? The center would be the same, roughly, and our spread would decrease. And that's because as sample size increases, standard deviation and therefore spread decreases. Okay, a lot of the time we like to ask you to interpret information from a simulation and draw conclusions from it. So Usually it's in the context of, do you think something is fair or unfair? Do you think this coin is weighted or not? Do you think the spinner is fair? And so forth. So similarly, let's say you have a friend that insists that he has an 80% success rate for free throw shooting. Curious, you decide to attend one of his games, and of his 20 free throws, he only made 10. So that means, keep in mind, his success that night was 50%. To test his claim, you ran a simulation of 20 free throw shots with a success rate of 80% 100 times, as shown in the distribution below. So keep in mind, this is based on his claim of 80% success. So this is the realm of possibility, essentially, of an 80% free throw shooter. Based on the results of the simulation, do you think he actually has an 80% success rate? If you just look at the simulation, this is what he did. What's reasonable for an 80% free throw shooter is more in this realm, okay? So I could take the mean, add or subtract 2 times the standard deviation and get a window, or simply just looking at this simulation, this is only happening 2 out of 100 times. That's 2% of the time. So essentially what you need to think about is, do you doubt your friend? The fact that on the simulation, a 50% of free throws being made only happen 2% of the time causes me to doubt my friend is actually an 80% free throw shooter. So I'm just going to write no. Based on the simulation, 0.5 or more extreme. Only occurred 2% of the time, which is less than 5%. So I doubt he's 80%. That's really poorly worded. I doubt he's an 80% free throw shooter. Squeezing that in there. Okay. So sorry, that was kind of squeezed in there. I took way too much space over here for the 2%. But let's say that on that night, maybe he made 70%. So I'm making this up. Okay, what if it was 70%? You're like, okay. I mean, that's not too far off from an 80% free throw shooter. I wouldn't really doubt him there. Even like 65%, you're like, all right, that could be his night. I mean, he could even do better. He could make all of his shots, even though that kind of seems unusual. He could make 90% of his shots, and you're like, okay, like that seems reasonable for somebody who says they're an 80% free throw shooter. But the fact that on that one night that you went out and looked, and he only made 50% of the shots, that's unusual. That's rarely going to happen based on random chance alone, so therefore it allows you to cast doubt. Okay, moving on to the next question. All right, I want you to pause the video right now and read through question 8. Okay, so I just highlighted some stuff that I felt was useful here. So the Gallup is claiming 50% of U.S. pay some attention to nutritional information. You went out and got a sample of 500 U.S. adults and found that 43% pay some attention. You then ran a simulation based on Gallup's claim that the true population proportion is 0.5. Okay, so this is the results of our simulation, again, based on a mean of 0.5. Using the results of the simulation, determine a plausible interval. So, based on this simulation, I would just simply take the mean, add or subtract 2 times the standard deviation, and I get this 0.456, 0.544. Okay, so this is what's possible based on the Gallup's claim of 50% of U.S. adults pay some attention to nutritional information. Based on the simulation results above is the sample data, so your 43% considered unusual. So basically, is it in the interval or not? Since it's not in the interval, this is considered unusual. So is this considered unusual? Yes. That's because 0.43 is not in the middle 95%. So does this cause you to question the true population proportion is 0.5? Yeah, it causes me to doubt it. So you actually went out and got a sample of adults, and you found that 43% said that they pay some attention to nutritional information. The fact that 0.43 is not in that interval is unusual. So it's unlikely that that would happen based on just random chance alone. So what that means is Gallup's claim of 50% is most likely not the case. So it's unlikely that the true population proportion is 0.5. Okay, so I jotted down my thoughts there, so just take a second, pause the video, and write those down. All right, take a moment here, pause the video, and read through question 9. Okay, so essentially you have two groups here. One group's been sleep deprived and the other has not. Their mean reaction times have been calculated, so 12.5 versus 9.5. You want to find if group 1 is significantly if their difference is statistically significant. Is it so drastic that something must have caused it to be that different? So we're going to do group 1 minus group 2. So 12.5 minus 9.5. And that gives me a difference of 3. Now, what they've done is now taken all the participants, shuffled them up, redivided them, taken the average of the reaction times, taken the difference, and plotted a point. And they did this 100 times. A difference of 3 or more extreme only occurs 1 out of 100 times. So 1% of the time, based on the randomization simulation, did a difference this extreme happen. So what that means is that this difference is statistically significant. Okay, so that means that sleep depriving our participants must have caused their reaction time to be that different. Now, if you were to have a difference of, say, 1, so whatever this time is, time in milliseconds, if your difference was 1, you're observing a difference, but it's not so drastic of a difference that it must be sleep depriving them causing it to happen. Okay, so you could observe a difference that might not be that special, and I'll show you what that looks like after I write down my thoughts for this one. Okay, so the mean difference in reaction time of 3 or more extreme occurred 1% of the time, which is less than 5%. This is unusual, so sleep deprivation must have caused this to occur. So anytime you come up with a result that is statistically significant, meaning it only occurs less than 5% of the time, that means that there must be something causing that to happen, so you can conclude cause and effect. All right, before I wrap up this video here, I want to show you guys this Regents question. So pause the video and read it. Okay. I'm going to show you how they actually make this simulation. Okay, so basically what they found is that there's tomatoes that were grown in a special mulch and they had a mean weight of 38.08. Then there were tomatoes grown in not a special mulch and their mean weight was 33.08. So their observed difference is 5. So what they would do is then put the tomatoes all back together in one bunch, re-randomize them into 2 new groups, so new mulch and new no mulch. Find the new averages, which you're seeing over on the right, so 35.38 and 35.77, taking the difference and then plotting a point. So they do this a bunch of times. Okay, and you can see the numbers changing. New mulch versus no new mulch. New averages calculated. New differences calculated. Okay, so anything in the middle towards 0, you'll see happens a lot. Now, anything out towards like negative 15 or positive 15, like those don't happen that often. Okay, so in your experiment, you had a mean difference of 5. Okay, so you observed a difference. Essentially, the question is that difference so special that it causes you to think, oh, it must be the mulch that caused that to happen? Okay, so when I look at the simulation, at 5 or more extremes seems to happen a lot. I mean, I could keep doing this for a long time. 5 is not that special. So you're observing a difference, but it's probably just due to random chance alone. So there may be something else causing that to happen, like maybe those tomatoes were just already genetically predetermined to be bigger. It might not be the mulch that actually caused that. Now, if you, in your one experiment, found a difference of, let's say, negative 15, so it actually has the worst, the opposite effect. Maybe your new mulch or your like black special mulch caused the other tomatoes to grow bigger, and you're like, oh shoot, I shouldn't use this mulch. That is statistically significant because you wouldn't expect that to happen very often, okay? Or in the other direction, like this difference right here, probably like 12, okay? If your difference in average weights between the tomatoes is 12 ounces, well, that's a pretty big difference that, based on my randomization, really didn't happen that often. So that means that it must be the mulch causing it. So pretty much anytime you find a result that's statistically significant, because it occurs less than 5% of the time on your simulation, that means that you can conclude cause and effect, and it must be your treatment causing that to happen, okay? But bringing it back to this Regents question, your difference of 5, not so special. Happens all the time, okay? So coming back up here, the correct answer here is 2. There was an effect observed, but it could be due to random chance alone or random assignments of plants into the groups. 3 and 4 were if you were to get a statistically significant result, which we did not, and 1 was there was no effect. Well, that's not true. We actually did observe an effect of a 5-ounce difference, okay? So it's just really, is that effect special enough to conclude cause and effect? Another way of thinking about it is, let's say you're playing a sports game, like let's say you're playing soccer and you're beating the team 5-0. Your friend scores another goal, so now it's 6-0. Is that goal, does it make a difference? Yeah, sure, you're 1 goal higher. But was it statistically significant? Is it a game-winning goal, essentially? Well, no, like we already were winning by 5-0. So when you're asking yourself whether something's statistically significant or not, it's got to be, is it really important that it made that much of a difference in your study? Okay, it allows you to conclude that cause and effect. All right, I feel like I've said a lot of the same stuff over and over again, so hopefully I didn't sound too terribly boring. But yeah, so that's pretty much your crash course in statistics. If you are interested in ever playing with this simulator, it's called Simulating a Difference of Two Means by Steve Phillips. Give it a search. All right, and I'm going to awkwardly end this video. Yeah. Okay, bye.